All right, time to get to my data collection. Whoa, what are you doing here? Whoa. This is a spaceship meant for one. Why are you on here? This is trespassing. I could get you arrested in space. As you can clearly see, we're very close to the sun trying to measure the black body emission spectra of this beautiful black body emitter. Why are you here? You know what? Regardless, I don't need no explanation. Just because you're here, I'm going to have to teach you science in order to rectify you being here and trespassing on my lovely spaceship. So without further ado, I guess we got to get into my presentation that I just so happen to have pulled up here called Rydberg and Ray's Catching the Light by me, your space captain, Zach Cook. Regardless, to start off, we have to kind of discover why black body emission spectra and measurements of speed of light are even important. And that's because it helps us identify the discrete line spectra for different atoms. And discrete line spectra are important because they're basically like fingerprints for an atom. They have specific wavelengths that are emitted based off of the relaxation of excited electrons in an atom's energy levels that are specific to that atom. So those wavelengths are going to be able to help identify specific atoms in molecules and structures, and even in analyzation chemistry for identifying specific atoms based off the wavelengths they emit. So that can be important in a multitude of regions in chemistry, and it's important to make sure that we identify these correctly and make sure that this is actually true and that energy is quantized, meaning that it's not continuous, but instead at energy levels. And how do we get there? Well, we use the speed of light. And in this experiment, we measured the speed of light by using a laser that was pointed towards a mirror that was spread out at different distances, and then proceeded to measure how far and how long it took that laser to get to an oscilloscope detector, which had these peaks that allowed us to be able to identify the amount of time it took, which obviously speed of light is measured in meters per second. So it helped us identify the amount of time it took for each distance. We then move on to black body emission spectrum, where we use black body emitters such as light bulbs in order to identify the distribution of wavelengths that each bulb created based on when it was lit. Each black body emitter emits at a different frequency based off of the material that's used in order to light it up, as well as the temperature, and that will help define where the max wavelength is for each black body emitter, which is what Planck's approximation, which we will see later, actually helped identify. And it actually is one of the main reasons why we know why discrete energy levels exist or quantized energy levels exist, which is why we are able to do the last part of this experiment, which is line spectra, which we'll get to in just a quick second after we note that the black body emitters were measured with an ocean viz spectrometer in this case, just with a spectrometer put up to each bulb that we wanted to test. And then we get to the line spectra that I just referred to, where a monochromator was used for deuterium and hydrogen, and a discharge lamp for each was lit up and put into the monochromator slit. And it was optimized for a range of 3,800 angstroms to 5,000 angstroms of wavelengths to determine at what wavelength these energy transitions spiked at. And we'll see an amplitude of those wavelengths for both deuterium and hydrogen later on as we actually evaluate that line spectrum. But again, you kind of see the emission spectra that we have here that produces different wavelengths based off of the energy that it takes for an electron to get excited at that energy level. So then we predict that the black body emitters that produced are going to be at the shortest maximum wavelength, which will result in hotter temperatures for the Wien equation. At least that's what we predict. And we also predict that deuterium's slightly larger weight is going to cause the overall max wavelengths for deuterium at those energy peaks to be slightly smaller than hydrogen, because it's going to take more energy to rip those electrons off of the larger atomic radii that we see with deuterium with one extra neutron. So as you can see, here's some equations. Most of these you've probably seen before, but the Wien equation is a little bit different. The Wien equation has the Wien constant B. The Planck's black body spectrum is used for Planck's overall approximation, which has the variables of Planck's constant, the speed of light, as well as Boltzmann constant K. And then the theoretical Rydberg, which the Rydberg constant was mentioned in the title, and it is how we help develop emission spectra for specific atoms based off of the wavelengths and the energy levels that we're trying to identify those wavelengths coming off from, is defined by this R value, which is defined by reduced mass, the E elementary charge, the epsilon zero vacuum permittivity, and the Planck's constant and speed of light. And you'll see where those are used later on in the results. So as we see the need for speed results, or the speed of light, we see that the laser is pointed here out through the lens, which will then go back to a mirror, which will then reflect it back onto an oscilloscope measurement. And as we can see, the average for, and there was an extra measurement right here that was defined by this reflection right here, which was back to the detector. And we'll see that the average for our speed of light is going to be a little different than the literature value, and that's because it's not in a vacuum. And that means that overall, the speed of light that we measured is going to have to go through the atmosphere. It's going to have to go through atmospheric molecules. So it's going to be a little slower as it goes through those gas molecules that we don't necessarily see in a vacuum that is perfect for measuring this exact type of quantization. But we only have what we have in the lab back on Earth. I know the spaceship seems incredibly technological, but we don't have that much on Earth. But anyways, we go to the black body emission stuff and we see that the black body emitter measurements for the spectrometer is going to be in the colored wavelength, and the Planck's approximation is in the white curve above it. And what you'll notice is that for the LED bulb and the condensed fluorescent bulb, especially here, the approximation isn't that good compared to the incandescent bulb and the halogen bulb. And even with those, it's still a little off. And that's because of two things. One, the LED bulb and the condensed fluorescent bulbs aren't actually black body emitters because they are not heating up a metal that is producing the light. LED uses different sets of smaller wavelengths in order to combine them and produce one white wavelength. And then the condensed fluorescent actually heats up gas in order to produce wavelengths, which is why it's so spaced out and discontinuous. Whereas the halogen and incandescent bulb do heat up a metal, but the reflectance from the bulb's glass of measurement of light is going to affect that approximation. And we'll notice here that as we move to the next one, that the sun outer atmosphere is the best approximation for this Planck's constant, which helps prove that the reflectance and the overall being of a metal black body emitter is what causes the Planck's constant approximation to be more consistent, because the sun obviously has very little reflectance as it's so bright. So we'll see now that the sun outer atmosphere is slightly different from the ground level, because again, our measurements from the ground level are going to be going through atmospheric pressures and different atmospheric ozone layers. So it's going to be a little bit off, whereas the outer atmosphere is a lot closer, and hence why we're out here right now looking at the sun, because we're very close and we're going to be able to get a great black body emission spectra. But that's going to take a minute, so we didn't add this in this report, but that's fine. So as we see, that kind of proves our point here in this chart. The Planck's temperature for the bulbs were more accurate for the max wavelength when the temperature was at its highest, which is a great conducive element to prove that the Planck's approximation is best for higher temperatures. And again, it was best for the sun's outer atmosphere. And as you can see, the Planck's temp even was different from the Wien's temp, which means that the approximation for Planck's temp can range a multitude of temperatures and still really fit that curve. So that proves that the outer sun's atmosphere is the best approximation for the Planck's approximation. So yeah, then we move on to the final results of this experiment, which is the line spectra. We see that there are actually 6 peaks. There's one down here that's very hard to see based off of this thickness of the line, but there's 1, 2, 3, 4, 5, and the 6th that I mentioned. And each of these peaks are like a snake's tongue, almost like a double splitted peak, where we see one that's going to refer to the deuterium peak and one that refers to the hydrogen peak. And we notice that the deuterium peak is actually going to be the one that is shorter in wavelength, which again kind of refers to it having slightly more energy. But since they're so close in atomic structure, it's not too far off from each other. And again, we notice that the 1H and 2H data is going to be very similar because they have very close to atomic structures. We do notice that the wavelengths are slightly smaller for deuterium. And we also notice that the energy values are slightly less for deuterium as we get up an atom in the energy levels. And that's because as we move away from the atomic nucleus, we'll notice that the energy levels in shells get closer and closer. So it's going to take less energy to transition from those higher energy levels that we see at 8 and 9 in comparison to 5 and 4 that we see at the bottom. And we wanted to make sure we get a good Rydberg constant in to identify and evaluate our experimental ionization energy and such. So we use this slope of 1 over wavelength versus 1 over n squared being the energy level. And we see that hydrogen has a less magnitude of slope compared to the deuterium. We are taking the absolute value, so the overall Rydberg constant is going to be around 1.08 times 10 to the 7th for both. But as we compare them to the theoretical Rydberg, which we use in this equation right here that we talked about before, we'll notice that the error is only 1.21% for hydrogen and 1.07% for deuterium. So our experimental values are very close to what we would expect for the theoretical values. And we also notice here that the ionization energy is slightly bigger for deuterium than it is for the hydrogen. And again, that is because the ionization energy is going to take a little bit more to get those electrons excited because of the pull that the atomic nucleus is going to have for being slightly bigger overall in comparison to the hydrogen. So that's going to affect the ionization energy for deuterium in comparison to hydrogen. In conclusion, we proved that both of our hypotheses were correct and that the smaller the wavelength, the higher the temperature for the black body emitters, and as well as the proven correct, we also proved correct that the wavelengths for each deuterium transition was slightly smaller and that the Rydberg constant was going to have a higher overall value in comparison to the hydrogen that we noticed. Now, why is this important? Well, we can help define what a black body emitter is, and we can help see using Planck's evaluation, how well of a black body emitter it is. So the sun is the best example, and we can use that reflectance factor that we talked about, as well as the temperature factor and the composition factor of the actual heating in order to identify which one's the best. We can also help define that energy is quantized based on the fact that we had those peaks for the specific energy levels for deuterium and hydrogen that were very close. And that can help with potential quantum mechanical techniques as well, like particle in a box, and identifying the wavelengths for each specific atom that we may see, and identifying those emission line spectra with the Rydberg constant that we created. Something that we could use better is honestly just identifying better intensities for the black body emitters that we found in the bulbs, as it was kind of hard to get those intensities to equal out, and we want those intensities to be equal out or as close as possible to make a better accurate and better measurements overall for our Planck's approximation. Either way, I'm going to go back to experimenting on my sun's black body emission spectra, and I hope you have a great day, even though you're stuck on the ship with me forever now. So, okay, bye.